Today's lecture is about thermal remote sensing and urban heat islands. This lecture is my favorite because this is the topic of our research the last years. Actually, the main topic of our research. We have other things, but this is really our favorite right now. What I'm going to do today is to tell you a story. Okay, I'll try to tell you a story and to follow the development of a system for the continuous monitoring of the urban thermal environment, taking all the steps from theory, from the basic principles, physics without really giving you the physics, but just the principles, the satellite measurements, the research that we have done, the application we have developed, the different products and how this can be used in different applications. And I'm going to show you the operational system that we have online and also a mobile application. Okay, so we're going to follow today all the steps for the development of a system from the basic principles to a mobile application for a user. Okay, let me start with a well-known figure which shows the radiation. So, in thermal infrared, what we are interested in is the radiation that is emitted from the Earth in thermal infrared. Okay, so the story is that we have the solar radiation coming from the sun, of course, that is coming through the atmosphere and hits the Earth, so it interacts with the Earth atmosphere system. A part of it is reflected, the rest is absorbed, and this radiation actually heats up the Earth, but the Earth stays at a constant temperature. We're going to say this in more detail later on. And due to this temperature, there is thermal infrared radiation that is emitted back to space. So if you had a satellite here, then this satellite would actually measure the thermal infrared radiance. So this is the basic principle behind thermal infrared, and now I'm going to give a few more details. Let's start with the very basic laws. Again, I'm not going to give any equations, but I cannot skip Planck's radiation law. So Planck's radiation law says that any object that has a physical temperature that is above absolute zero emits electromagnetic radiation. What wavelength is the spectrum of this radiation has to do with the temperature of the body. Actually, here we have a terminology we call a black body. A black body is a hypothetical source of energy that behaves in an idealized manner as it absorbs all the incident radiation and none of this radiation is reflected. So, then, due to its temperature that has to be constant, emits back some radiation, all of this radiation, and this is only a function of temperature. So this is the definition of the black body. Planck's radiation law gives you the distribution of intensity as a function of wavelength. For what? For different temperatures. So if you had a black body with a temperature at, say, 3000 Kelvin, then this small line is actually the function that would show you the intensity for every wavelength in the spectrum. As this temperature goes up, as this temperature increases, then firstly you have more radiation, and this is something quite important. So the integral under the curve is actually more, it's actually increased, it's actually higher. So you have more radiation, and also you can see that the maximum moves to a different wavelength. So this we're going to see in a different slide. The other thing that I wanted to stress here is two particular temperatures. One temperature that is important for the system that we are interested in is around 6000 Kelvin, which is the temperature of the sun. So for the temperature of the sun, this is the yellow curve is actually what gives you the Planck's what is given by the Planck's radiation law. So this is the distribution of intensity as a function of wavelength. The other temperature that we are very much interested in is the temperature of the Earth. The temperature of the Earth, okay, varies, but we can say that it is around 250, 300 K. So this is a completely different wavelength range. So if you notice here, this is a logarithmic scale on the x-axis on this plot, and this here peaks at around 10 microns. Again, we're going to see this in more detail. Here we have Wein's displacement law, and this simple equation is like probably the only equation I'm going to show today. So what Wein said is that as black bodies become hotter, the wavelength of the maximum emittance shifts to shorter wavelengths. This is exactly what we saw before. So as you have hotter black bodies, the wavelength of maximum emittance is shorter. And this is actually the case again here for the sun, and this is invisible because this is where it peaks. And for Earth is the thermal infrared. So the top curve is actually the radiation that is emitted from the sun. Not all of it reaches the Earth because some of it is absorbed by atmospheric windows in the atmosphere. And keep in mind, always in remote sensing, that visible is the wavelengths that our eyes are tuned to see. Okay, so in essence, visible is the radiation that is acquired by our eyes. We don't have eyes in thermal infrared. For this, we need special cameras. Okay. Again, the two famous curves. By now, I think we have already understood what it's all about. So let me just repeat that the emission from the sun corresponds approximately to a black body. You can remember 6,000 K. This is close enough. And this gives a peak emission at 0.48 microns, which is in the visible spectral range. In the case of Earth, the surface temperature ranges from about 240 K to about 315 K, with the most common temperature of about 300 K. So you can remember 6,000 for the sun, 300 for the Earth. This corresponds to peak emissions at this wavelength, which is approximately 10 to 12 microns. If you see, if you notice the spectral bands in thermal infrared of the satellite sensors, these are essentially near 10 microns and 12 microns. The good thing, okay, one more. So, in essence, the radiation that is emitted by the sun reaches the Earth. All these wavelengths reach the Earth. A part is absorbed, but please notice here, as Earth is not a perfect black body, actually, it's not a black body, you do not have equal absorbance for all the wavelengths. You have different absorbance for the different wavelengths. And subsequently, the rest is reflected. Okay, so you have the incident beam, you have a part that is reflected, and the rest is absorbed. Because of the absorbed radiation, if you didn't have another mechanism with which the Earth could actually emit back the radiation, then you will have a constant increase of Earth temperature. But this is not the case. So the temperature of the Earth remains constant, and radiation is emitted at a different wavelength, which is the 300 K that we saw based on Planck's law. Okay, now the good news is, if you recall, we said that in thermal infrared we are interested at around 10 to 12 microns. The good thing is that 10 to 12 microns are in this spectral region, and here if you see the transmittance of the atmosphere, you will see that here we are in the region of an atmospheric window. This is very important because if you were at different wavelengths where the transmittance was low, then you wouldn't be able to have thermal infrared sensors to measure the temperature of the Earth. Okay, so it is very important that you have your sensors at these wavelengths where you have atmospheric windows. Otherwise, you wouldn't be able to use this technology. Okay, yet life is not that easy because you have some more components, radiation components, when we talk about thermal infrared radiation. So the dominant component and the one you're interested in is your target, is the radiation that is emitted by the surface, because you actually want to measure the temperature of the surface. So the dominant component here, the dominant radiation component, is the one that is surface emitted. But the atmosphere has some temperature. It's above absolute zero temperature. So by itself, it emits radiation downwards, which reaches the Earth and is absorbed, and upwards. So what you actually measure, absorbed and reflected. So what is actually measured by the satellite is not only this component here that is emitted by your target in what you're interested in, but also you have the effect of the atmosphere, because the atmosphere is also emitting. So if you're interested only in this part, you have to have some corrections, some atmospheric corrections, like you also need to do in your visible and near infrared part of the spectrum, which is more known to us because we are more familiar to this. Okay. The other problem that we are facing is that the land surface emissivity is not equal for all wavelengths and for all different surfaces. So if this is the radiation of the black body, where the emissivity is 1 because you would have a perfect emitter here, so epsilon here would be equal to 1. Here, you don't have in Earth, you have a selective radiator, so this curve here is not the same. So you have different values for radiation depending on where you are in terms of wavelength and what kind of surface you have. And this is the emissivity. These are emissivity spectra as a function of wave number. This is emissivity as a function of wave number, which is the opposite of the inverse, rather, of wavelengths for different surfaces. Okay. The other interesting thing is the so-called Leslie's cube. This is the radiance that is measured by a thermal infrared sensor. You see, these are different. Whereas here, the temperature map shows that these two sides of the cube have the same temperature. But the thing is that they don't have the same radiance. Why? The reason is that they are made of different material, and this is actually gives you a different radiance. So when you're actually measuring the radiance, you cannot infer the temperature unless you know the emissivity. It is very important that you know the emissivity of the material for this particular wavelength in order to derive the temperature. Otherwise, this information is combined. You cannot measure the temperature. Okay, I just want you from all this to remember 4 key points. One is how radiation is absorbed and reflected in the short wavelengths, and as a result, emitted by the Earth at a different wavelength because the Earth has different temperature. Okay, and this is emitted in the thermal infrared, and this is actually the principle why we can actually measure the temperature of the Earth. The second point is to remember these 2 curves. One is for the Sun, 6,000 K, the other is for the Earth, 300 K. And the one of the Earth peaks at around 10 microns, and this is very fortunate because we are at an atmospheric window. This is the reason why we can measure this radiation from satellites, because it can pass the atmosphere and you can get a signal. Otherwise, if you were here or here in the white regions, you wouldn't be able to have a satellite and get a signal. It would be all absorbed by the atmosphere. So these are the 4 basic principles that are behind thermal infrared remote sensing. In terms of measuring so now we go to the next step, which is the measurement. Here you would have different ways of measuring the land surface temperature, and this would be, for example, ground observation. Okay, we are not interested in that. Low altitude data that you wouldn't have much influence of the atmosphere. High altitude data in which you would have quite significant interference of the atmosphere, and satellite data where you would have all the signal from the Earth and the atmosphere. We are mostly interested here in satellite data, and you have two kinds of orbits where you would have thermal infrared sensors. You would have sun-synchronous satellites, the polar orbiters. They are lower in the Earth. They cover the whole Earth, and then you would have the geostationary satellites that are much further away from your target, 36,000 kilometers, and you would call it a geostationary orbit. And surprisingly, what I'm going to be showing you later on, and the system I'm going to be showing you later on, is based on data from geostationary satellites. It's not based on data from polar satellites. I believe that most of the applications that we have done until now are based on polar satellite data. One problem that you also have to deal with in thermal infrared is clouds. And the reason is that when you have clouds, they would emit radiation because they have a temperature above absolute zero, so they do have a temperature, they emit in thermal infrared. Therefore, what you would have if you had clouds, you would have this kind of image where the bright pixels correspond to areas with high temperatures, and with high temperatures, and the dark pixels correspond to pixels with low temperatures, and of course the ones with the lowest temperatures in this scene is clouds, because they are quite high in the atmosphere. So this is what a thermal infrared image, a real thermal infrared image looks like, and this is due to clouds. So when you have clouds, you cannot do anything. One parameter that is really central in thermal remote sensing is the estimation of land surface temperature. Land surface temperature is not the same as air temperature. In general, what we are mostly familiar with is air temperature, because air temperature has to do with our discomfort. Air temperature is the temperature that is given, in the weather report. This is what we know. The land surface temperature is something different. The land surface temperature is essentially the skin temperature of the Earth, and it has very much to do with the surface materials. Whereas the air temperature has more to do, it is very much correlated to land surface temperature, although in a very complicated manner, and it's not, you cannot describe this with equations, but also you have the effect of the local meteorology for air temperature. Here you see a composite of different land surface temperature images. This is a clock here giving you the timestamp. All these recordings are in the same day. So what I want to stress here is that the land surface temperature is something that is really changing a lot during the day. So one of the things is that you cannot just take one image in the morning and that's it, you are covered with the temperature. It's as if you had the temperature, you had a thermometer giving you one estimation at 10 o'clock in the morning, and then this would be enough for you to understand what the temperature will be during the day. It's not the case. So you really have to have continuous monitoring. And this is the reason why we tried to exploit the geostationary datasets instead of polar orbiters. Because with polar orbiters, you have only one pass, and then maybe you will have two passes in the day, but this does not give you the diurnal evolution of temperature. So the reason why we shifted to geostationary data is because we actually wanted to get the signal of this dynamic change of land surface temperature. And this image is from geostationary orbit, because you see it is always centered at the same location above the equator. It moves with the same angular velocity as the Earth. It is above the equator. Particularly, this satellite here is Meteosat satellite. It is centered at 0.0, so 0 latitude, 0 longitude above here at an equatorial plane, and it moves together with the Earth. So as the Earth rotates, the satellite rotates with the Earth with the same angular velocity, and this gives you the opportunity to monitor the area of your interest continuously. So when we talk about continuous monitoring of an area, we talk about a weather satellite that is a geostationary satellite. Okay, with polar orbiters, you do not have this temporal resolution that is required. Another example, I just wanted to say this before I move to the next slide, is that when we talk about land surface temperature and air temperature, I want you to recall in the summer, when you walk barefooted, then this is the land surface temperature. So if you walk on the asphalt and it's really very hot, and then you see some grass and you jump because your feet are burning, the air temperature is the same. The land surface temperature is completely different. On asphalt, you cannot stand. On the grass, is fine. So the temperature differences are really very. You have discrete changes between land covers, whereas air temperature is much smoother because we're talking about a fluid. With land surface temperature, the changes really are discrete and abrupt, something that does not happen with air temperature. For LSD retrieval now, if you recall, we said before about how the land surface temperature and the emissivity are coupled together. So when you measure the radiance, really you measure both of them. So if you want to infer the land surface temperature, you really have to know the emissivity. Let me just explain why the problem is ill-posed here and unsolvable and underdetermined. So the thermal infrared radiance, which is a known because you measure it, so you have it, is measured in n channels. Usually you have 2 channels, for example. And the unknowns are n plus 1 because you would have n surface emissivities in each channel because the emissivity is a function of the wavelength, so you would have the emissivities in each channel, and LST. LST, of course, does not change with wavelength because LST is the temperature of your object. So you have n for the emissivities, where n is the number of channels, plus 1, which is basically what you want to measure, which is your land surface temperature. So you have to work your way around this problem. So you have the LST retrieval methods. There are 2 families with many algorithms under each family, and we are not going to go into any detail on that. LST retrieval, when the emissivities are known, because, for example, you know for your for your object what is the emissivity, because you know very well what is the material of your surface, and then very easily you can calculate the land surface temperature. You either have single channel methods, and these are very popular, for example, with Landsat data. Landsat has Landsat PM and DPM Plus have thermal infrared data, but have only 1 channel. So single channel methods were actually developed for Landsat because it is for 1 channel. And you have multi-channel methods where this is quite common. You have the split window methods, and you have multi-angle methods. For example, when you have a satellite that is moving, it's taking one measurement forward, then it passes over the area of interest and takes another measurement in the vertical, in the nadir, and then as it moves away, it takes another measurement at the back. So you would have 3 consecutive measurements of the same target from 3 different angles. The reason why you need that is also because of the atmosphere. If you take it, the measurement in 3 different angles, then somehow you can estimate the effect of the atmosphere. But if you do not know the emissivities, Then you have another family of algorithms, which are stepwise retrieval methods and a simultaneous retrieval of LSD and emissivities with or without the information about the atmospheric conditions. This is not very common. Usually we work in these methods, and I would say that from all these, the most popular ones are the multi-channel methods, especially the split model. Let's say a few words about the LSD retrieval accuracy, because, okay, we can measure the land surface temperature, but what is the accuracy that we need? The problem with the accuracy usually come from the problems that we have to estimate accurately the emissivity and the atmospheric conditions. These are the main causes of inaccuracy. So the better you know your emissivity for the different materials that are present on your scene, and also the atmospheric conditions, the better it is for your retrieval. The more accurate you would estimate your land surface temperature. So these are the two things that you have to take into consideration. But another thing that I want to stress here is that when you have a pixel, it is very important to understand that you don't have a point measurement. You actually have a measurement over an area, and this area is the size of the pixel. It can be 100 meters by 100 meters, 1,000 meters by 1,000 meters, or even 5 kilometers by 5 kilometers, which is the case for the geostationary satellite. You can imagine how difficult it is to estimate the emissivity for a pixel of 5 kilometers by 5 kilometers, because clearly it is a mixed pixel. So you have to take into consideration the temperatures and the emissivities for each particular area within the pixel. And this is quite difficult. So usually you would have an effective emissivity for your pixel. And this really illustrates also the fact that if you measure against a point measurement, again, although this some authors think it is ideal, on the other hand, it's ideal only if you have the ideal conditions, and this is to have a very large homogeneous area. What you see here is not the best example to look at the urban heat island. We will see other examples during the lecture. But here, I just want to stress that these do not heat up and cool down with the same rate. So these patterns are really changing during the day. Another very recent and very interesting product is the global geostationary land surface temperature product. This is a Copernicus product. It is available online if you are interested. So basically what they do here is they take data from 3 geostationary satellites that are above different areas. One is the Severi that I have already talked about. The other one is GO satellite, and this is above the Americas. And the other one is MTSat, that is, it is above Australia and Japan. So what they do is that they try to make an image by taking the 3 satellite images and make one single image, and they do this at hourly steps. So this is a very important data set. It's quite new, and it is available online. It's not available in real time, but it is available online. So if you want to take the data and process it in post-processing mode, not in real-time mode, you can visit Copernicus services. Another interesting thing here that we have already talked about is the spatial versus the temporal resolution. This is a problem inherited in all satellite data. So when you have when you increase the spatial resolution, so the course would be 3 to 5 kilometers from Severi, and then you would go to 1 kilometer satellites. The most recent one is Sentinel-3, SLSTR, and then to Landsat and Aster, and that's it. This is the threshold. You cannot go any better with thermal infrared. But at the same time, you would see that for the geostationary satellite that has this coarse resolution, you have an image every 5 minutes. So as you increase the accuracy on the ground, you decrease the acquisition frequency. And this is a very common story in remote sensing. This is always the case with all the data. One reason to compensate is to have a fleet of satellites. So for example, if you had quite a few satellites at 1 kilometer resolution passing over the area of your interest at different times, then you would be able to have a better and more usable data set for the diurnal evolution of your land surface temperatures. Again, and something that we didn't say as we have condensed the material for this lecture, is that if you have this kind of satellites, with different overpasses, you have different angles of acquisition. So one time you will see Athens on your right, the other time you will see it on your left, the other time will be at nadir. So these different acquisition angles give you a different LST distribution because you are looking at different sides of the same object. For example, if you had a mountain, you would see the side, so if you are looking at the side that is facing the sun at the time of your acquisition, then this would be warmer than the other side of the mountain. So it depends where the satellite is with the sun and the slope and the aspect of your terrain. This is quite complicated in terms of geometry here. Okay, I think this I have already covered. What I need to say here is what I have said a few times, that you cannot have it all. You have to either choose for spatial resolution, for example, or for spectral resolution, or for revisiting capability, or for spatial coverage. You cannot have it all. Another interesting thing that we want with thermal infrared, it is obvious, but maybe you haven't thought about it, is that with thermal infrared, we don't need the presence of the sun, because you would always have thermal infrared images because of the temperature of the Earth. You don't need the sun to get a thermal infrared image. Okay, I know it's obvious what I'm saying, but we are very familiar with morning images. We are not so familiar with night images. So with thermal infrared, we have images night and day. This is something quite important. In terms of budget, usually thermal infrared images are free. And now, since the last lecture where we discussed about how free is free data in remote sensing, now that Aster has become a free data set, actually I tweeted that a few days ago, all thermal infrared data now are free. It means that you don't have a satellite with thermal infrared data that you have to pay for. As we said, thermal remote sensing is the only means currently available that can provide a continuous and simultaneous view of the city's thermal environment. This is the case. I think that I have convinced you by now that satellite data is the only actually means to do that. Aircraft data have many problems. Really, it is the temporal resolution that is not adequate, because you don't have scheduled campaigns over the area of your interest. Then you have the high spatial resolution thermal infrared sensors from Landsat and Aster, and then you have this is actually one image like this. This is an image from Landsat, and this is early in the morning. This is it's 9 local, no, it's 9 DPC. 9 DPC. This is again one image that was acquired during the Thermopolis 2009 campaign that I mentioned before, and you can see that at this time the city center is not actually the most hot area of the city. One of the as we have already said in different lectures, one problem of urbanization is that people have actually replaced natural materials with artificial materials like the asphalt and cement. these materials have completely different thermal characteristics, thermal behavior than the natural materials, which is like a forest or a shrub or even open spaces. And this has actually changed the character of the thermal environment. Okay, so the urban heat island is actually induced by humans due to the replacement of the natural materials by artificial materials. It is a phenomenon that you can see it in almost every city. The patterns that you see differ between cities, and the reason is that the different surrounding areas. So, for example, if you have Cairo that has desert around the urban area, or if you have an area, a city that around it has, for example, a forest, then the spatial patterns that you will see, the thermal patterns that you will see in the urban area will be different. And this has to do with the different rate that a surface is heated up and cooled down during the day. So the urban heat island is actually the phenomenon where the urban center is warmer than the surrounding areas, which could be suburban areas or rural areas. This difference can be a few degrees, as high as a few degrees. The reason why the measuring and the monitoring of the urban heat island is important is because it has a very strong effect in thermal discomfort, especially during days that are very hot, like heat waves, for example, in heat waves. It has been published, it is a well-known fact that during heat waves you have increased mortality and morbidity, and the urban heat island, because your population actually lives in a city and is concentrated in an area that the temperature is even more elevated due to the urban heat island, means that the urban heat island itself increases the discomfort and then increases the mortality due to the heat wave. So it is linked. Another side effect of the urban heat island is the increased energy demand, especially when you have heat waves, and also the increased energy demand causes blackouts. This is quite common. For example, in Greece, we are very, very much familiar with blackouts during heat waves. There are different types of heat islands that you will find in literature. I'm not going to give you details for all of them because different researchers are interested in different measurements. But basically, you have two different urban heat islands. One is the atmospheric, and the other one is the surface. In general, when we talk about the atmospheric urban heat island, we talk about the air temperature and the differences in air temperature between the center and the surrounding environment. And when we talk about the surface urban heat island, we talk about the land surface temperature and the difference how the land surface temperature is higher in the city center compared to the rural areas or the suburban areas. So this is what I want you to remember here. Also, you can remember that atmospheric urban heat islands are usually measured by the stations, and one important aspect here is that because the meteorological stations, the standard meteorological stations of the standardized networks are measuring air temperature at 2 meters. This is usually the air temperature at 2 meters above the ground. That this is what you measure and you take as atmospheric urban heat island. Whereas for surface urban heat island, usually it is the land surface temperature that you measure from the satellite. But then here comes a question, and this is, although it is quite simple, there is no unique answer. Exactly what do I have to subtract to measure the intensity of the urban heat island? Okay, it's the difference between the urban and the rural, but do I take 1 pixel in the urban, 1 pixel in the rural and subtract it? Do I take the maximum urban and the maximum rural and subtract it? Do I take the whole urban area, take the average, the whole rural area, take the average and subtract it? So this is, although so simple, it is one of the most common problems that you will find with this kind of research, because different researchers use different definitions. And the problem with this is that then you cannot compare the results, because one researcher has used one definition and the other has used something else. So always when you read this kind of papers, you should pay attention to what exactly it is defined as the urban heat island intensity. Okay, data needed. So you have high spatiotemporal urban temperature data sets. This is actually what you would want to have, as we said before. You want high temporal, high spatial resolution. But this, as we said, if there is a trade-off in remote sensing, you cannot have this combination of high spatial, high temporal temperature data sets. So there is a lack of data. There is no system that can give you the data that you want with the frequency that you want and the spatial resolution that you want. So what is the challenge here? And this is the topic of research of our group. The challenge is to take 4-kilometer land surface temperature data from geostationary satellites and actually downscale it down to 1-kilometer satellite. This is what MODIS image would look like. But this is not a MODIS image. This is an image taken from geostationary satellite, Meteosat, and with appropriate processing, we have downscaled it to 1-kilometer satellite. So this is a major topic of research. This is very important because it means that actually this kind of data, we can have it with 5-minute spatial resolution. Whereas with MODIS, you would have 2 or 4 images per day, depending if you take 1 or 2 satellites. So one area of research is the spatial enhancement of land surface temperature derived from geostationary satellites, so that you keep the signal for the temporal frequency and you downscale it to the resolution that would be very similar to MODIS resolution. Okay, this is the original data, just Europe. Just briefly, how we do the downscaling. We will not use any equations here, but I just want you to understand the concept. So let's imagine that we have 2 worlds. The top world is the fine scale world at 1 kilometer. This is what we want to achieve. And the bottom world is the coarse scale world, which is 3 to 5 kilometers. Here we never say one exact number. Maybe you have noticed that during my lecture, because the spatial resolution of Meteosat image depends on the angle where you are in the image. So if you go towards the edge of the Earth disk, the resolution is degraded. If you are at nadir, near 0.0, the resolution is 3 kilometers. So this is why we say 3 to 4, 3 to 5 kilometers. So this is the reason why we do it. Okay, so we start with this image. This is an image of Attica at a coarse resolution scale. This is what it looks like without much processing. This is a set of what we call predictors. So it is a set of data that gives some information at the desired fine scale. So this data comes from different sources. For example, layers that could be relevant is land cover, for example, where you would have agricultural land, urban, vegetation, water. Again, topography is quite important, so you would use a digital terrain model. You would calculate the different aspects, north, south, east, west, and slope. These are all derivatives from topography. You can have a vegetation layer from NDVI, and you can have emissivity layer from MODIS, for example. Let me just stress here that land cover is quite constant. You wouldn't expect many changes in land cover very frequently. Topography is very constant, of course. Vegetation, though, and the vegetation index are not constant. They change with season a lot, and they change at a temporal scale of, say, a couple of weeks. And emissivity, again, is not constant, and the reason is that there could be changes in the vegetation that would cause again change in emissivity, and this is just one example. Okay, I don't want to go too much into this. So you have the predictors, your components at fine scale. So the first step is that you degrade the resolution of your components and you take them to the coarse scale world. So this is easy because you just smooth it and you take it to this coarse resolution. The next step is that you combine the components at coarse scale with the land surface temperature at coarse scale, and you make a regression model. You see how these components are compared with the land surface temperature, and by this combination you make a regression model. The selection of the regression model is key to the success of this methodology. There are many papers on that. But once you have the regression model that combines, that gives you a relationship between the features, the components, and the land surface temperature, then you can go back to the fine scale and use this regression model with your fine scale components and get a modeled fine scale land surface temperature. So this is the concept of how you do it. So again, as I said, the regression of the model is really very complicated, and I'm not going to cover it here. If you want to go deeper, for our methodology, one of the first papers that we published was this one in IEEE. Okay, so by using this methodology that I just described, now we have land surface temperature at this scale, and I'm going to demonstrate our system later on in the third part of the lecture. We have this kind of images every 5 minutes. So it's as if you have a MODIS overpass every 5 minutes. When we first started downscaling the images, this was summer 2014. This was the first summer that we did it. We did it with M.Sc 3, severity data from M.Sc 3. Now we do it with M.Sc 4. The difference is that now we do it with M.Sc 2. M.Sc 2 gives images every 5 minutes. M.Sc 3 gives images every 15 minutes. Again, because it is quite too many images. Here you have one day, 24 hours, by taking hourly images. And this is the day of the year, the land surface temperature for June, July, and August. If you see the black dots represent one acquisition from M.Sc severity, for which we have this kind of image, and the red triangles represent MODIS terra, and the blue triangles represent MODIS aqua. So if you didn't have the black dots that are giving you the diurnal evolution, it's not necessary that you would be able to retrieve it from MODIS LST. This is a very fancy image that Panagiotis has created. When we try to, this is one of our very recent papers, to see how with this downscaling, I'm just reminding you here, the area that we're looking at, for this paper was Rome. We want to see if the time series that we retrieve, because now we are interested not in a single image. We don't want to see only how good we have done this downscaling, like on an image basis, but we want to see it on a time series basis. And this is quite important because we are talking about thousands of images eventually. So we want to see if the patterns that we see in the coarse resolution images are kept after the downscaling, because for us it is quite important to see this kind as a measure of success of our methodology. And here we see during 24 hours. So imagine this as a clock. We start here. This is night time, so you have a well-defined urban heat island. Rome center is the square in the middle. And what you see here is an index that shows you how good a pattern is formed. Let me put it this way. Okay, so you see that the pattern in Rome center is very well formed during the night, and then after sunrise, which is approximately here, approximately here, then it starts disappearing, and actually in the morning you have the so-called urban sink. Urban sink is when the city center is actually cooler than the surrounding area. This happens because the materials of the urban center do not heat up so quickly as the surrounding, maybe agricultural, rural or suburban areas. And as I said again, this has to do with the city and its environment. So as time goes by, this is not very intense, but then this is sunset here, and after sunset, again you have very well formation, very good formation of urban environment. So it changes during the day. We have evaluated our results against Landsat, which is an institution, which is a data set, well, it's a system, it's a platform in Portugal where they have a validated product for the course resolution. And these are the red dots. This is the one-to-one correlation line. The x-axis is our own retrieval for land surface temperature at the original resolution. These are the red lines. And then the downscale against MODIS. So the black dots are for nighttime, and the gray dots are for daytime.